All right, Discrete Math, how are you? Good, 2-5, watching a video. Maybe you are right now. You have for homework numbers 8 through 20, from section 8.1 on partition numbers and Stirling numbers, etc., etc. That was erroneously referred to as 8 through 10 on homework due like last week or some crap like that, and I fixed it so you were supposed to do that. So please do that first, then watch the video. Woo! All right, can we do this in like 5 minutes? I think we can. Number 8 says, I have a large bowl of identical candy bars. Whoa, it's like I wrote this problem. 4 young trick-or-treaters have just knocked on my door and are holding their bags out for some candy. If I grab 6 candy bars from my bowl, in how many ways can I distribute all 6 of them? Okay. Wait, I kind of blanked for a second. Yeah, so the kids are standing there with their bags open, so you can tell which kid is which. So that's like a thing. So I have 6 candy bars, and I'm distributing them to the 4 children. So now this sounds very stars and bars-ish, yeah? But, wait, how many candy bars do I have? 10. I have 6 candy bars. Okay, so I have 6 candy bars, and there are 4 bags. All right, but does every kid necessarily get a candy bar? No. Maybe not. So wait, let's do the problem in 2 ways. What if we're being nice, and indeed every kid gets a bar? Just to do it that way first. Then we have to give every kid a bar, so then we have 2 bars left, yeah? And again, we stars and bars with but in this case the bars are stars, right? So there are 4 bags, which really means 3 dividers, and there are 2 objects to distribute among those 3 dividers, so that's like 5 choose 2. So yes. Good. Now, if instead we are not nice, or rather, I don't know, some people have a rule, if a kid is not dressed in a costume, they just won't give them a candy. That's like a legit thing. Some people do that. Yeah. So, what if their outfit is distasteful or something, right? All right. So wait, quiet. So if not every kid gets a bar, that's still just stars and bars. But now we have 6 plus 3 dividers, so 9. Yeah, total objects, and 9 choose 3. Cool? Okay, good, that's pretty easy. Good, number 9. Number 9 says, Jody has 12 identical boxes of Girl Scout cookies. She plans to sell them all to relatives. If she has 6 candidate relatives, in how many ways can she unload the cookies? You may assume that some relatives may decline her offer, but that all the boxes will be sold. So this is basically how many ways can I pawn off the 12 boxes of Girl Scout cookies to the 6 relatives? This is also stars and bars, yeah? Yeah. So I have 12 boxes, and then 5 dividers between my 6 relatives, so that's 17 choose 5, or 17 choose 12. All right, good. 2 down, so many to go. Number 10 says, a technology company is moving to a new building with an excess of space. The company has 11 programmers on staff. If the new building contains 2 identical office suites, each large enough to hold up to 10 programmers, in how many ways can the programmers be assigned to suites? Okay, if the suites are identical, then it really doesn't matter which suite you end up in. The suite is determined by who your suite mates are, effectively, right? So this is basically asking how many ways can we split up 11 programmers who are all distinguishable from each other naturally into 2 teams. Well, we have a thing for that. It's S11-2. Stirling numbers of the second kind. S11-2 is the number of ways of dividing 11 distinguishable objects up into 2 non-empty containers. Good, say good. Good. Okay, good. Number 11. A library has 4 identical display cases that are used to promote new acquisitions. This month, and someone's going to move the camera as I move. You don't have to do it yet, but eventually. Yep, this is all being taped. Try to smile or adopt your standard expression. In libraries, 4 identical display cases that are used to promote new acquisitions. This month, the librarians wish to promote 9 books. They do not want any empty display cases. In how many ways can the books be displayed? Dude, this is, wait, hold on a second. They are identical display cases. So, that's a little bit weird. So that's, I will assume by that that you cannot tell them apart.
Yeah.
Although that's like a little marginal because like they have to live somewhere. Maybe they're floating around. Yes. Good. Anyway, this is basically how many ways can I put 9 different looking books with different covers into 4 sort of spots, and the answer is S94, although I'm not in love with that, it's a little vague. All right, well, what's up?
How is S94 vague?
I know, I just don't totally like that you can throw in the word identical display cases, but
You think the problem is
really, I think the problem's vague, correct, yes, I think it's, but moving on. I hesitate to say that Gossett is being a little sloppy. Yeah. Good. 12. No, I did 12 already. No, I did 12. I have 7 new quarters that I wish to place into my 2 front pockets. I really don't care which pockets the coins end up in. In how many ways can I pocket the quarters? So, how do we do this? So I'm just dividing up the 7. I'm basically just partitioning my 7 quarters into 2 piles. So this is, but it's not quite that because, so that would be like P72, yeah? The number of ways, but I think I have to add 1 because P72 is like the number of ways of doing it with just, where they have to be some quarters in each pocket. But I claim that like you could also just P71, which is that really just 1, right? Yeah.
Wait, don't you have like 2 because the other pocket can also
the 2 pockets?
No, but I don't. I'm sort of asking like it doesn't matter which pocket is which. All that matters is like how many ways can I like yeah. All right, moving on. All right, 13. What's up? No, they're all indistinguishable quarters. Even though they have like that's the other thing. They have like serial numbers and stuff, but like. No one looks at those. This is pre-state quarter revolution. All right. An English professor has chosen 5 novels for a course in contemporary literature. Each student must choose to write an analysis of at least 1 of the novels. Extra credit will be given for every additional analysis. There are 6 students enrolled in the class. Give a numeric count of the number of ways the students can submit reports. All right. So you have to write 1. But like you just get extra credit, and you just keep getting more extra credit, man. So every different new extra credit is like a new way of submitting your final report. So what this effectively boils down to is, of the 6 novels, 6 novels? No. 5 novels. Every single possibility would be a different thing. So there are 2 to the 5th equals 32 possible like submissions. Minus 1 because you're not allowed to submit no book reports. Right? But now, wait, I'm not done yet. I'm not done yet. Now, the question actually asks, given numeric count of the number of ways the students can submit the reports. In other words, how many different ways could the whole plot have turned out? Well, as there are 6 different students in the class, and each one of the 6 students in the class could have done completed the assignment in 31 different ways. This is 31 to the 6th. Yeah.
That's a lot.
Do you follow that? Yeah. 31 options for each kid. There are 6 different kids, and each way the different ones. 31 minutes. All right. Yeah, good. I think we're good. All right. 14. What is the 14? It is. Mei Ling received 3 identical laundry bags as high school graduation presents. She has brought all 3 to college. If she has 20 pieces of laundry, in how many ways could she stuff the bags with all 20 pieces of dirty laundry? Alright, now the laundry is presumably distinguishable because no one would have just a whole bunch of identical shirts. That would be weird. What's up? Good. So basically, she has 3 laundry bags, and how many ways can we put the laundry into the 3 bags? So this is S21 counts the number of ways to put, well, which is just 1, man. But that's the ways to put all the laundry into just 1 bag. Plus S22 represents all the ways of putting the distinguishable 20 objects into 2 indistinguishable laundry bags, plus S23. And there's nothing that says that she has to use all laundry hampers, so we need to consider all possibilities. Do you agree?
Yes.
Okay, good. 15. Yeah. 15 people are going to attend a picnic. Shirley is packing 1 ham and cheese sandwich for each of these people. She will carry the sandwiches in all 3 of her red and white checkered picnic baskets. In how many ways can Shirley bring the sandwiches to the picnic? Alright, so she has 3 red and white checkered picnic baskets, but they're all being jostled about or whatever, they're all indistinguishable from each other. So this is essentially just, I hope, yeah. How many ways can I divide 15 objects up into 3 baskets where no basket is empty? Good thing we have a symbol for this. It is P15-3. Good? Say good. Good. 16. What's up? Yeah, might have to go take a peek. I'm probably still in frame, but go turn it a little bit. 16. Jeff just went shopping and bought his parents an anniversary present consisting of 8 blue towels. The cashier told him that she had 4 white bags available for carrying the towels home. In how many ways can Jeff bring his towels home, assuming that Jeff does not have to use all the bags? Okay, well, if he does not have to use all the bags, then this is essentially I have 8 towels, and I need to distribute these 8 towels to 1 or some or all of the bags. So P84 would be the number of ways to distribute the 8 towels through 4 bags. P83 would be the number of ways to distribute them through 3 bags. P82 through 2 bags, and P81 through just 1 bag. It's legit to leave it like that, but if you want to be cool, you can also, let's see, how do we remember this again? Oh yeah, we get temporarily 4 extra towels for a total of 12 towels. And then P12, what the hell am I doing? P12-4 would be the number of ways of dividing up the 12 towels into 4 bags, none of which are empty, but some may have only 1 in it, right? And then if at the last second the dude's like, no, I only want 8 towels, not 12, then if he takes 1 out of every bag, then that counts the ways of, so that's why that's that. Cool? Alright. Good. 17. Suppose you are going to design 6 blue t-shirts. You have 9, oh, this one's hard. You have 9 pictures that can be ironed onto the t-shirts. A lion, a cat, a flower, a heart, a moon, a star, a person, a palm tree, and a dolphin. You could make some pretty awesome t-shirts with those objects. Good. In how many ways can t-shirts be created? Assuming there are no boundaries concerning the number of pictures to be placed on each t-shirt. Okay. Alright. So, what's up?
Can't you just 1 lion, 2 lions, 3
No, because if you have never ironed patches onto t-shirts, Reynold, you know that when you iron it on, you use it up, man, and it's gone. That's how ironing patches onto t-shirts works. Someone back me up on this? Yeah. So you have literally 9 things, and they're 1 use only. Yeah.
Oh,
Yeah.
wait, what?
Yeah. So the question is, how many possible t-shirts could we have made? But we only get to use, there's only 1 dolphin iron-on, man. Then if you use it up, you gotta go buy another one. Alright. So, this effectively boils down to I have 9 pictures, and I can do whatever I wish with these 9 pictures. Wait, hold on, I gotta think for a second. You have 9 pictures that can be ironed on. Right, so I might not even. Damn it. I'm placing distinguishable objects onto indistinguishable blank white t-shirts. But I guess, wait. Built into the problem is some kind of idea that we're going to use them all, right? Yeah. Okay, due to the law of it would be less than awesome to not use all of your patches, we're going to use all the patches. So if we're going to use all 9 patches, they're one use only, and we have 6 t-shirts, that we're clear on what the problem is now? Okay, good. So what could we do? Well, we could distribute the 9 patches to the 6 t-shirts so that at least every t-shirt gets at least 1 patch. That would be the number of ways to do that. But there's no one that says there's nothing that says we have to do that. We might distribute the patches to just 5 t-shirts, and we might distribute the patches to just 4 t-shirts. How are we feeling about this? And then at some point I stop. No, I think I just keep going all the way, right?
You could just have like one super
I could use summation notation. That would be good if I did that. Too late. What's up?
One super awesome t-shirt and a bunch of boring ones.
That would be this one. Yeah, it would be 1 super awesome t-shirt and 5 blank ones. That's what I would do if it was my team. Alright, good. 18. Suppose you are the boss of a small company. You have 3 distinct jobs that need to be completed next week by people on your staff. Stuffing envelopes, copying files, and typing. Woo! S, C, and T jobs. They're pretty fun. There are 7 employees who will each be assigned one of these jobs. At least 1 employee must be assigned to each task. How many ways can you assign the jobs? Okay, so if you have 7 employees, and the employees are by convention, distinguishable because they're like humans, then essentially what I need to do is I need to make sure that, yeah, so now like the containers are sort of like the 3 jobs, right? Yeah, so there's like an S job, a C job, and a T job, and I need to place like the employees into the containers in such a way that none are empty. But also it matters who does what. So what we do is we temporarily think of the containers as being unlabeled. And there are 3 ways to put the 7 distinguishable employees into the 3 indistinguishable containers. Then subsequently, I can choose 3 factorial ways to label the 3 unlabeled containers SCT, hence, like, making them now assigned to a particular task. Bob? Woo-hoo! All right, 2 more to go. 19. The people in charge of a raffle are going to give out 4 prize bags to the raffle winners. They want to make sure that each prize contains at least 1 of the 11 gift certificates for a department store. And how many ways can the prize bags be prepared? Assuming that all gift certificates are of the same monetary value. So these are just identical freaking gift certificates. So we just gotta, this is just peel out
Different
4.
department stores.
No, I think they're just the same department store, man.
Oh.
It's a
Yeah, for a department store. Good, that one was kind of boring. 20. Let's see what Meg is doing. She decides to throw her 10-year-old daughter, Sue, a birthday party and allows her to invite 15 friends to the house. Meg purchases 25 red balloons for the children, since red is Sue's favorite color. In how many ways can the balloons be distributed to the children at the birthday party, including Sue, assuming that no child should go home without a balloon? Alright, so that means there are 16 kids total, yeah? Because like the 15 friends plus herself. And then this is just stars and bars, this bar. There are 25 balloons, and so there are 15 dividers, so there's, wait, I just went wrong. Oh, every kid has to get a balloon first. Yeah, that's right, sorry. So there are 25 balloons, so distribute, and now there are only 9 balloons left. And now you just stars and bars those 11 balloons into the 16 kids. So that's 24, choose 9. Alright, how are we feeling about this? Go to the last 7 minutes of class. We shall do number 25. Okay, let's go. TNK is defined to be, this is a number like sort of like combinatorial primitive, the number of ways to partition a set of n elements into exactly k non-empty ordered subsets. Number of ways to partition a set of n objects into exactly k non-empty ordered subsets. Non-empty ordered subsets. And all right, step one, prove that. So A says prove that Tnk is k factorial times Snk. Okay, well, just duh. Okay, because that's just what you do, right, man? You have them unordered and then you just like order them. Okay. All right, so that's like done. And do you see that if I can somehow get an explicit formula for T of Nk, then I'll have a formula for the Stirling numbers, right? Wow. Right, so good. Now, so the bulk of the proof, or the only really part of the proof to do, is this formula regarding an explicit formula for Tnk. I put explicit in quotes because it involves like summations and like alternating, and it doesn't seem particularly awesome to me, but
explicit, though.
it's still pretty good, yeah. -1 to the, actually I take it back, it's great. -1 to the I, k choose I, k minus I to the n. Alright, so why is this true? And then he gives a hint, and this is for blah 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 blah. There are k to the n ways to get the partitions of empty subsets that are allowed. This contains illegal partitions. So subtract the number of partitions with at least one empty subset. Now adjust for overcounting, etc., etc., etc. Okay, let's just do this. Can I just? This makes my brain hurt a little bit, so I'm gonna just like do it with. What's going on? Do it with an example. So example, and then generalizing is just the exact same thing, just a little more general. So take Tn4. Okay. So what I have are 9 different objects. What should they be?
Cow.
Those 9 pictures.
Suppose I have 9. We have 9 polyhedra. And what we are going to do is we are going to split these polyhedra up, and we're going to give them to 4 different orphanages. It goes to 4 different orphanages. All right, and Tn4 counts the number of ways to do this because the orphanages are all different, and etc. Good. Okay. All right. So, but we must give every orphanage at least 1 polyhedron. Agree?
Yes.
Okay. So, because it would be cruel to deprive, the west side orphanage of a polyhedron. All right. Well, first, what we could do is give away think of all possible ways to pass out the polyhedra. So this would be all possible ways to distribute the polyhedra. But as I just said, that is too many because we need to we're not allowed to not give an orphanage polyhedron. So let's subtract the ways in which 1 container is empty, basically, right? So in which at least one orphanage gets no polyhedra. But now we have also over subtracted because we might, if there was a, right?
Yeah.
Yeah. Because if there was, wait, why did I over subtract?
What if there's one? Because what if there's
oh yeah,
Like-
because if there's a one of the original ways to distribute in which 2 orphanages didn't get their didn't get polyhedra, then I counted that twice. It's not obvious that it counts twice. Let's like start as we go. So how many ways are there to distribute the polyhedra just like straight up? 4 to the 9, because for each polyhedron, there are 4 choices of which orphanage we send it to, yeah? Okay, so now we need to subtract out all the ways in which at least one orphanage gets no polyhedra. All right, well first, let's, how the hell do I do this? Just
choose an orphanage.
staring right on my paper, but I don't get it.
Orphanage.
Yeah, choose an orphanage, and there are 4 choose one ways to choose one orphanage, and let that orphanage be the orphanage that doesn't get any polyhedra. Oh yeah, that's dumb.
And then 3.
Okay, so then there are 3 to the 9 ways, therefore, to distribute all the polyhedra. Because now you're distributing the 9 polyhedra. You have 3 choices for each polyhedron, because you've decided to not give it to the other orphanage, right? But in doing this counting, in some of these ways, you may have also given no polyhedra to like an additional orphanage, right? In which case you've double counted. Because if you first didn't give any polyhedra to orphanage A, but while counting that, orphanage C didn't get any polyhedra, then you've now double counted because you've now also counted the one where like C doesn't get the polyhedra and then A doesn't as well. So we need to add back in all the ways in which at least 2 orphanages, etc., get no polyhedra. How many ways to do that? Well, plus 4 choose 2 ways to pick which 2 orphanages get no polyhedra. And now the 9 objects, there are 2 choices for each of them, yeah? And then you've now overcorrected again. And you need to subtract out 4 choose 3, which is just 1, which is the way in which you, which is 4, which is the way in which there are 3 orphanages in which there are no, that receive no polyhedra. What's that?
4 choose 3 times 1.
Yeah. Oh yeah, that's more, that's like maybe like more pretty if I do it like that, times 1 to the 9, and then this is like 4 choose 0. Yeah, that's more pretty. Alright, good. Wonderful. Say goodbye to period 5.
Period 5.